I studied two of the most important proteins on Earth. Without them, life on Earth as we know it couldn't exist. These proteins fuel ecosystems by providing energy for nutrients and habitats. They produce nearly all the oxygen in the atmosphere that you and I breathe, and they're a nearly endless source of renewable energy. You see these proteins every day when you go outside and see a towering tree or your neighbor's lawn. These two proteins are photosystem 1 and photosystem 2, and they're responsible for photosynthesis. Now, photosynthesis is almost synonymous with plants. Seeing a dense jungle or rolling fields of corn like this is seeing photosynthesis in action. You might be surprised to learn then that the majority of photosynthesis on Earth isn't actually performed by these land plants, but instead by photosynthetic microbes like cyanobacteria shown here that live in soils, lakes, and oceans. You might be even more surprised to learn that all these organisms, ranging from the smallest microbe to the largest tree, all perform photosynthesis using the proteins photosystem 1 and 2. Because of this, studying any of these organisms deepens our understanding of photosynthesis across the board and can provide inspiration to improve it. Recently, it's been discovered that certain species of cyanobacteria are able to modify the photosystem protein structure in a process called forward light photoacclimation. These changes allowed them to use forward light that traditional photosynthetic organisms can't use, something I show on the right using colored light bulbs. This is really special because for decades, scientists believed that photosynthesis could only occur using certain light. These cyanobacteria break that mold, and there's been a lot of excitement in trying to understand how they work. I've studied this by directly looking at the protein structure of these forward light or FRL photosystems using a technique called cryoelectron microscopy. Together with some colleagues, I used an electron microscope that's so powerful it allows me to see the atoms and bonds that make up the protein structure. The photosystems are essentially little machines, and looking at the protein structure is like opening a watch and seeing all the gears and springs inside that allow the watch to keep time. Using this technique, I've identified the precise location of each atom in the protein, and my results reveal that at several very specific locations, the chlorophyll have been altered in these forward light photosystems, something I show on the far right. Now, chlorophyll are the pigments in the photosystem that actually absorb the light, and so altering the chlorophyll changes what light is absorbed for photosynthesis. So my results, which identify these modified chlorophyll, is a big step forward in understanding how these cyanobacteria are able to absorb and use forward light for photosynthesis. But just knowing what and where the changes are doesn't quite tell the full story. My colleagues and I are continuing studies to tease out the subtle principles that dictate the location of these altered chlorophyll that I've identified. We hope that these studies can inspire new methods to improve photosynthesis by applying some of the principles we discovered to grow crops like corn in new ways.